Let's prove the calculus product rule using the definition of a derivative. First thing we want to do is to talk about the different ways that derivatives are shown in different textbooks. This is one common way here, where the derivative would equal the limit as a approaches x of f of a minus f of x over a minus x. Another way that it's often shown is what I call the delta x notation. I somewhat prefer this notation, so that the derivative in this case would be the limit as delta x approaches 0. In other words, this value is getting smaller and smaller here, of f of x plus delta x minus f of x all over delta x. Another way this can be shown is that instead of f of x, we're going to assume that at x our function takes on the value a, and at x plus delta x our function takes on the value a plus delta a. So that in this case our derivative is going to be the limit as delta x approaches 0 of a plus delta a minus a over delta x. So back to finding the derivative of a product. So we have a function f, and it is equal to the product of a function u times a function v. So using the last notation that we referred to, so at the value of x, our function u of x is taking on the value u. Our function v of x at x is taking on the value v. At x plus delta x, it's v plus some delta v. And our u of x function at x plus delta x is taking on some value u plus delta x. So to find f at these 2 points, so f at these points, at f at x, I'm going to say at x, f equals u times v, which is rather intuitive, and that at x plus delta x, it's really the same sort of thing, that the value of f, we come up here, we see that this is u plus delta v, or u plus delta u, and v plus delta v. It's the multiplication of those. So u plus delta u times v plus delta v. So this is a simplified picture of what we just found. So again, for a function that's equal u times v, our 2 points that we need in order to compute the derivative, one is here, another is here. U times v, and u plus delta u, and v plus delta v. So just quick review of definition of a derivative. When it's with respect to x, we would look at it in this fashion. And if it's not with respect to x, it's just taking on the value a, where f of x equals a, or f of x plus delta x equals a plus delta a. The definition of a derivative would look like this. So reminding ourselves of the latter form of what the derivative would look like when f of x equals a, we now just, this is then the proof. So we would just substitute in our values for a plus delta a and a. So here we're doing the multiplications of the first term, u plus delta u times v plus delta v minus the original function, again following the definition of the derivative. Then we simply take a FOIL of these above terms here. We get u v delta u v plus u delta v plus delta u delta v minus uv. These will cancel. Now we'll split these up into three pieces, and we'll see that we end up with v delta u, u delta v, and delta u delta v, each of those over delta x. Thing to note here is this last term. This is going to approach 0 because the numerator is two very small numbers being multiplied together. They will get smaller much quicker than a singular term like we have down here on delta x. So in getting rid of this last term, we end up with the proof, if you will, of two numbers multiplied together, or two functions multiplied together. So I'm going to just end showing that there is a proof. There is a proof to, if you do want to do it with respect to x, this can be done. I don't think it's very informative, but here it is. The tricks here, if there are tricks, is to do this. Basically, you're adding 0 here, where they're doing this so that they can form a derivative. That, as you'll see down here, if you actually wanted to go through this. The next thing that you need to observe is that this portion right here, as delta x approaches 0, this v of x plus delta x is just going to approach v sub x, thereby yielding you the same thing.